So, some parting thoughts about correlation and regression. So, these are great ways to find relationship between variables and discuss about how strong that relationship is and how good of a relationship it is. But they do have limitations and you do need to be aware of them. So, let's run through what some of those things are. The distinction between explanatory and response variables is important. Input and output does matter. You can see a plot for the non-exercise activity versus fat gain. We looked at that earlier in the section. That has a standard deviation of the residuals being 0.739 and the R squared is 60.6. If we interchange the X and the Y, interchange the explanatory and response, you see now that S, the standard deviation of the residuals, is 167.37. That's a significant difference. But think about why that would be. It's different units. We're measuring the residual in the same units as non-exercise activity. Over here we're measuring the residuals as fat gain. Much smaller units that we're dealing with. So the biggest change is that you have to pay attention to what the input is for the regression equation. They're drastically different. Second, correlation and regression lines only describe linear relationships. When we talk about the correlation, we are talking about a linear relationship. When we talk about a regression line, I hope you're saying, well, yeah, we're talking about linear relationships. It's a line, for crying out loud. We can't use these techniques for data that has a curved trend to it. Correlation and least squares regression lines are not resistant. Remember, that means that outliers dramatically sometimes affect what's going on. So here's a graph, a plot of age at a child's first words in months. So 20 months, 30 months, 40 months. Child 18 was just over 40 months before they said their first word. And then we have this Gessel score. We also have the residual plot over here. Notice there's no overwhelming pattern. Child 19 is significantly different. Child 18 not as much. But if we take away those outliers, without child 19, without this child, we have this red line. Notice that it doesn't change a whole lot. But when we take away child 18, this outlier, the line changes quite a bit. An outlier that is not very different horizontally, but it's more different in a vertical nature, isn't going to affect our regression model as much as removing an outlier that is dramatically different in the explanatory variable. If we cover up child 18, notice that all of our points are really closely grouped together, and it's quite a bit more difficult to get a good direction for the line if we're just eyeballing it. But if we take away 19, that child 18 still influences the path of that line. That line still goes very close to child 18, and it's still on sort of along the same path that we were at first. An outlier is an observation that lies outside the overall pattern. Points that are outliers in the y direction but not the x have large residuals. Other outliers may not have large residuals, and we see that back here. Child 19 has a very large residual. It's an outlier in the vertical direction. Child 18 is an outlier in the horizontal direction, but notice its residual is still fairly small. An observation is influential if removing it would markedly change the result of the calculation. Points that are outliers in the x direction are often influential for a least squares regression line. So that's what I was talking about back here. Removing the horizontal outlier dramatically changes our regression model. So that point is influential. Child 19, that point is not influential because removing it doesn't make a dramatic change in our line. And finally, association does not imply causation. Even if we have an explanatory variable and a response variable that are very strongly associated, they're very strongly correlated, there's strong correlation, we have a very good line of regression, that doesn't mean by itself that changes in X actually cause changes in Y. It could be due to any number of other confounding variables. So it's something to be aware of, that association doesn't imply causation. Correlation and causation are two very, very different things. So here we have an example. We have a study. People with 2 cars live longer than people with only 1 car. Owning 3 cars is even better, and so on. There's substantial positive correlation between the number of cars and length of life. Why? Why? Well, is it really the cars that cause people to live longer? Probably not. Just because you go out and buy 500 cars, that doesn't mean you're going to live the longest. That should make sense. You should be thinking, yeah, that's ridiculous. But why would people with more cars live longer? Well, they probably have more money and thereby can afford better health care and just all-around quality of life. So there is an example where strong correlation doesn't mean that we have causation between the explanatory and response variables. So finally, a summary from section 3.2. I want you to take a look at these things and make sure that you're feeling okay about what the things in bold mean. The summary is pretty long here. We did a lot of things in this section, but that concludes section 3.2 and our linear regression analysis of data. Have a wonderful and wonderful day.